Welcome to February 23rd's LeetCode Challenge. Clone graph. Given a reference of a node within a connected, undirected graph, return a deep copy clone of the graph. Each node in the graph contains a value integer and a list node of its neighbor. So we have this this node class here that has the property of value of int type and a list node called neighbors. So test case format. For simplicity, each node's value is the same as the node's one index. For example, the first node of its value of equal to 1, second node's value is equal to 2, and so on. The graph is represented in the test case using the adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes a set of neighbors of a node in the graph. Given the node, it is always be the first node with value equals to 1, or assigned to 1, I should say. You must return a copy of the given node as a reference to the clone graph. So example, say you have the original graph here where you have a connected cyclic graph, right? You have, I believe that's a cyclic graph, and you want to basically create a clone. So you can't return the same graph because it is the same graph. You can't clone the nodes, but the graphs are out of order, right? You can see this is one's connected to 2, which is connected to one's also connected to 4, and you can't return out of order. So it has to be a clone where the nodes are new and the graph looks the same, i.e. the clone graph should have clone nodes connected to the same nodes of its neighbors. That's pretty much it. So say we're given the adjacency list of this graph right here. So we see 2 is connected to 4, 2 is connected to 4, 1 is connected to 3, 2 is connected to 4, and 1 is connected to 3. I think we're given this graph right here. Nope. Let me see. 2 is connected to 4, 1 is connected to 3, 4 is connected to 2. Oh, okay. So there are 4 nodes in the graph. So the value of, I believe this is, so let's see, we have the first node being value of 1, his neighbor's node is value of 2, and the fourth node's value is 4. Makes sense? And the second node is located at its neighbor, its value is 2, his neighbor is 1, the third node is value 3. And the third node is value 3, neighboring node is value 2 and 4. So yeah, there you go. Let's see. So that's adjacency list. If you're not familiar with adjacency list, it's basically a collection of unknown lists. I mean, it gives you basically the list as a matrix almost, or an array of an array. So we're given this actually this adjacency list is this graph right here. So another example is given a index of 0 or nothing inside it, return the output which contains one empty list. The graph consists of only one node of value 0, does not have any neighbors. And an empty graph does not have any nodes. So our constraints are that the node's value ranges between 0 to 100, as given here as well, 1 to 100, and the number of nodes range from 0 to 100. The value is unique for each node. There's no repeating edges, no self-loops in the graph. And the graph is connected and all the nodes can be visited starting at the given node. So this one is ranked medium. It requires you to know a little bit about basically graphings and know what adjacency list is and know how to manipulate or traverse through graphs. So we're given a graph problem. So the first thing we want to do is be able to clone a graph. That means that you need to be able to traverse through each node and copy the value and make a node out of it. So there's a couple ways to traverse through a graph. You can use a depth first search or breadth first search. So one of them is the depth first search should be using a stack, and the breadth first search should be using a queue. It doesn't really matter which one you use. Both have similar type of pros, different types of pros and cons, but similar time complexity, that is. So let's say we choose a depth first search, so therefore we're going to use a stack, right? And even that, in that case, we can use either we use a stack because it's similar to a Python list. And then once the graph could have cycles in it, we want to track the nodes that we already visited. For instance, the cycle right here. If you've been to a node already, we don't want to add it back to our new list, our new copy cloned list, I should say. So we could use that using a set, right? And that's pretty much the code. Let's type the code to traverse the list. So I'll break it up to steps. First, we want to clone, traverse the graph. So let's say visited. That's going to be a set. It's going to store all of our nodes that we have already visited before. And we're going to use a depth first search. Therefore, we're going to use a stack. And the stack is going to contain a list of nodes called nodes. All right, a variable nodes, I should say. Next thing we want to do is, while the stack is true, we are going to have called the current node. We're going to assign that, we're going to pop it from the stack. Stack.pop. And then we're going to add the visited to our node to our list. So visited.add. I'm going to add the current node. So that's pretty much it. Pop from the stack and add to the list if we have already seen it. So we need to be able to basically traverse the graph this time. So for each, let's call it. So since we have a neighboring node here, we're going to might as well implement this class above for each neighbor. In the current node dot neighbors, we are going to find if the neighbor is not in visited. So this is, if it's not in visited, then this is to prevent cycles basically. If it's already in our visited, then we don't want to add it again. If it's not in our visited, to prevent cycles, we're gonna, if it's not visited, we're gonna add it to our stack. I mean, not append it to a stack, I should say. Append the neighbor to our stack. Neighbor. So that's pretty much it, how we've traversed the graph and basically appended to a stack, which is depth first search. So this is not the code. It's not the code for the answer, but it is an approach, right? So everything here should look somewhat reasonable. So next thing we want to do is copy, create a deep copy, a clone. So how do we build a graph from adjacency lists? So we can create one and build from it. So we create a list and then add it to a pair for each edge, basically. So basically, next thing we want to do is create a system where we can add our adjacency list to. So let's say we call this adjacency list. What am I doing? This is going to be a list or an array. And then before we add to the stack, if we already popped it for each neighbor, what we want to do is append to our adjacency list. And to do that, we need to append our current node value, node.val, and our neighbor.value as well. And let's see, this needs to be removed, and So what we did was we adjacency list. So for each, we created an empty adjacency list here to initialize it. Then for each adjacency list, if we popped it and we added to the visited node, what we want to do is add it to our adjacency, append it to our adjacency list, and we want to append the tuple of a current node value and a neighboring value. So that seems fair. Not in visited. Yep. All right. Then we want to be, now that we have adjacency list, and we want to build a new graph using the adjacency list. Right? How do we build a graph? So there's a lot of things we could do. So first thing we want to do is think about, let's say, so if we could use a hash map of the values to nodes to the nodes of both as a lookup node and also the keys to the visited value, that would be a good idea. And then instead of building the adjacency list, why don't we just connect the nodes as we see them, right? So we don't need this at all. I mean, we do need it, but it gave us the idea that, hey, why don't we just build it as we go along? So in order to do that, let's first of all, actually, let's put this handling of an empty graph first. So if node is none, so this handles an empty graph, return none. Alright, and then do we even need our visited set? The answer is no. We could just upgrade that to, let's see, we have a stack. So what we could do is combine what we just did, combine our visited set with our adjacency list to make a hash map out of it. So let's erase those, and then we're going to define a clone hash map. So we're going to call it clone, and we are going to create a set of hash map. So it'll be node.value, which being the key, and then the value will be the node itself. So it'll be node.value. So basically replaces the visited set we had before and the adjacency list, combining them both together. This increases the space complexity, for one thing, because we have both a lookup of the nodes and the key value as the node as well, due to the property where we have index 1 right here. This makes it really simple for us to use a hash map. And then while stack is true, what we want to do is, let's call this, I'm going to erase this part right here. And then see the current node stack.pop for each neighbor in the current node neighbors. We don't need this part anymore because we're not adding to the adjacency list. What we want to do, however, is update the key value of our cloned hash map, which is going to be the neighbor.val, and that's going to be the key value to the node of neighbor.val. Alright, that should make sense. And then we don't need our neighboring, since we're don't have visit array anymore. What we could do is we could still stack.append.neighbor, so to keep track of the visited node later. So that's still good. And then we want to exit this for loop so that we could connect the node to its neighboring new graph. So once we have a copy of the new node and the graph as well, we want to connect the edges together. And we could do that outside, within the while loop, but outside this for loop. So what we want to do is say clone current node I should call it n maybe, would have been better. Value, val I should say. That's underscore. So update the clone value dot neighbor neighbors dot append. So we're gonna append the new neighbors to the cloned the new graph. And to do that, we just append it with the current node, which is going to be the key value of using the key value of neighbor dot val. So basically connecting the node to its neighboring neighbors in the new graph. If all my spellings are correct, that should work. All right, and then at the end of this, we just return. What do we return? We return our clone. Our clone at the node.value. Right? Okay. Let me see. No, this is not right. This should be clone. Clone. Alright. Not scriptable. Let's see if there's an error in there somewhere. If node is not none, handles the empty graph, return none, that works. So we define a stack called node with the list node to do depth first search. We define a clone hash map that replaces the adjacency list and visited array I've set. So that'll be node.value, which is the key, and then the value will be node.val. While the stack is true, I'm just going to click enter there. What we want to do is update the current node with, we want to pop it from the stack, and then for each neighbor in the current node.neighbors. Alright, I forgot to mention that we gotta create if the neighbor dot value is not in the current in the clone. So you want to create a new node if we haven't seen it in the clone hash map yet. So what we could do is tab all this, and this should work. Looks promising. All right, let's go. Whew. All right. Time complexity is big O of, let's see. We have each time complexity is big O of the stack size plus the for loop as well. The new old node and let's call it big O of n squared. Let's just call it that for now. Space complexity is big O of let's see, big O of, well, it's the hash map, so big O of n, whatever the hash map size is. Alright, that's it. It's quite a tough one. It's quite long too. Alright, have yourself a great day, guys.